Hey everyone, my name is Atharva Kelkar. I'm a graduate student in the Van Lehn group at the University of Wisconsin-Madison. I am very happy to present to you some of the work that we've been doing when combining molecular dynamic simulations with machine learning to predict interfacial properties. The property that we're going to look at today is hydrophobicity, which is the thermodynamic tendency of a surface to minimize contact with water. So when you place two hydrophobic surfaces in water, they tend to aggregate and come together to minimize contact of the surface with water. One example of this is polymer collapse, where you have some hydrophilic domains and some hydrophobic domains, and the hydrophobic domains tend to come together and collapse to form a hydrophobic core, which minimizes the contact of these hydrophobic domains with the surrounding water molecules. Another example, which is a real life application, is something like surface fouling, where you have a surface and because of hydrophobic aggregation, a foulant keeps on accumulating on the surface, and this can eventually lead to a compromise of structural integrity or the formation of a biofilm. And this can be avoided by tailoring the hydrophobicity of the surface. And we've seen this in a variety of other phenomena and applications. For example, there's protein folding, nanoparticle absorption, molecular recognition, colloidal aggregation, and a ton of other applications. So the question is, how do you measure how hydrophobic or hydrophilic a surface is? And classically, what people have been doing is looking at contact angle measurements. So you have a surface here, and you let a droplet of water form on the surface, and then you measure the angle theta between the surface and the interface of the water. And if your theta is between 0 and 90, you say that the surface is hydrophilic, and if your theta is greater than 90, you say that your surface is hydrophobic. But the issue is that this is a macroscopic measurement, and what we are interested in as a group is to study nanostructured materials. So to measure the hydrophobicity of nanostructured materials, people have come up with AFM-based techniques where you measure the contact force of your AFM tip with the uh, nanostructured material of interest with and without water. But the issue is that these experimental techniques are very time consuming. They're also very resource intensive, and they don't give you a good molecular picture of what's happening on the surface. So what people have done is that the community has come up with computational methods that have led to a insight at the molecular level, which is difficult with experiments because it's very difficult to zoom into that level of resolution. And also there's a control over factors that are experimentally difficult to control. So for example, there could be patterning on the surface or chemical heterogeneity that you might want to control, which is difficult to do experimentally. One particular computational advance that we're going to be talking about and using a lot in this talk is something called indirect umbrella sampling. So in indirect umbrella sampling, what happens is that there is a surface, for example, a self-assembled monolayer, or a SAM in this case, with some water molecules on top of it. We apply a bias to de-wet a cavity near the surface, and we measure how easy or difficult it is to de-wet this cavity. And we call that free energy of de-wetting this cavity or hydrating this cavity, if you take a negative sign, as the hydration free energy. And what has been observed is that this is an order of magnitude faster than experiments, and it also gives you an incredible level of molecular control. And the time to do this is around 65 nanoseconds of simulation time, which would be around 15 to 20 hours on a good supercomputer. So the main takeaway that I want to give you is that while experiments are time consuming and computational methods are faster, these computational measurements still take up a long time. So each measurement still takes around 15 to 20 hours. So the question that we try to ask is it possible to use data-centric tools to reduce this time needed to measure the hydrophobicity of surfaces? And what I'm going to be presenting is going to be this theme. So I'll first try to motivate why molecular dynamics is a great opportunity to use a lot of these new modern machine learning methods. So if you look at a typical molecular dynamics simulation, you have around 10 to the power 4 molecules, and each of these molecules will have like distinct positions and velocities, and then you keep on simulating these molecules over and over again for say t time steps, and t could be on the order of like 10 million time steps. If you combine all of these together, you have almost 10 to the power 11 data points from one molecular dynamic simulation, and that is a lot of data. And this gives us the perfect opportunity to use data-hungry machine learning models as you see in modern machine learning or deep learning applications. And we're going to use exactly this property of molecular dynamic systems to build upon. But first we went back to our understanding of hydrophobicity and tried to gauge what is important when we want to predict the hydrophobicity of a surface. And there is a theory that tells you that if you look at an extended hydrophobic surface with some water molecules on top of it, the hydrophobic response of this material comes about because of a rearrangement of the water network. And to study the rearrangement of this water network, what is very important is to understand and study spatial correlations in water structure. And this could give us an insight into how hydrophobic or hydrophilic a surface is. And another thing that has been shown to be very important is enhanced density fluctuations at this interface between the water and this material. This interface behaves like an air-water interface, and that is characterized by enhanced density fluctuations. So it's important to study both spatial and temporal correlations to understand how hydrophobic or hydrophilic a surface is. And to do this, a very good machine learning model is convolutional neural networks. So the whole idea that we want to work with is that you use convolutional neural networks to learn spatial and temporal correlations in interfacial water structure, and then you use those learned features to make predictions of how hydrophobic the surface is. So to build an ML model, we first need to generate training and test data. Then we need to see how you can convert an MD trajectory into an input for the ML model. Then you can rationally build your network architecture of the machine learning model that you're using. And then we can train and cross-validate the network and see how well a network actually performs. So let's come to the first step. So the first step is generating training and test data. So when you want to generate data for a machine learning model, there are some prerequisites or some good to haves in the data that you want to generate. The first is that it should span the entire range of surface hydrophobicity. So you don't want it to be biased towards, say, the most hydrophobic or most hydrophilic surfaces. You want data that is evenly spread out through this whole range. So you don't only want to sample the extremes, you want to sample everything in between at even intervals. So you don't get biased towards any one end or to a particular set of values. So what we did was, we took a set of different molecules. We built self-assembled monolayers from these molecules, and these are long carbon backbone ligands with an amide, an amine, and hydroxyl end groups. And then we scaled the charges on these end groups shown in blue to vary the polarity of the surface and in turn the hydrophobicity of the surface. What we see is that we can sample a very nice range of hydration free energies from the most hydrophobic, which is around 30 to 40 kT, to around 100 kT at the upper end, and we do this in very uniform intervals of hydration free energy. So this is a very good data set to train your model on and to also see how your model performs using a cross-validation approach, which we'll come to in a few slides. The second question is, you've been given a molecular dynamics trajectory. How do you convert it into an input for a machine learning model? So firstly, we're given this simulation with a self-assembled monolayer and a ton of water molecules on top of it. So we can't possibly parse through all of this data. So what we do is we select water molecules near the interface, which we define as interfacial water molecules. And these seem to be the most important in determining your hydration response or your hydrophobicity. We look at these molecules from a top-down approach. So if this is if these are my molecules, I look at it from a top perspective. We grid these molecules into NX and NY bins, and then we convert these into density maps of only the oxygen atoms. And so that would give us a single frame. What I can do is, I know that temporal correlations are important, so I can stack different frames together to give it a notion of temporal correlations, or I can average frames together to give it a notion of spatial correlations. So I have captured some sort of a notion of temporal and spatial correlations just by defining my machine learning input in that way. One more thing that we can do is, instead of just stacking things together, we can stack these frames together as well as add another channel of information. So what we also did was, to this oxygen density, we also added a channel of hydrogen density, and this representation is something we call the hydrogen representation, which also encodes information about orientation as well as temporal correlations. So now that we have rationally thought of some physically informed data input representations for our ML model, we actually want to build an ML model now. So to build an ML model, we use a convolutional neural network. What a convolutional neural network does is that it convolves over your complete input to find patterns, and then it relates these patterns to your label, which in our case is a hydration free energy. So I would like to look at this very briefly in two distinct steps. So the first few sets of layers would be called the feature extraction layers, where you try to extract the important features from your image. And the final few layers would be your function approximation layers, where you take your features and then relate them to a label using a function approximator or an artificial neural network. And just as a reminder, the input here is the input from the MD simulation. So this could be a stacked, a single, or a hydrogen image, an image, or like a data matrix. And your label in this case is a hydration free energy, which we get from our INDAS calculations. And you could also do this with a 3D CNN. So the difference between a two-dimensional and a three-dimensional convolutional neural network is that this will identify patterns in two or three different axes. So it won't just look at the X and Y axes of your planar image. It will also look at your axes in the temporal dimension. So when you stack images, a 3D CNN is a great way of also identifying spatial as well as temporal correlations. Okay, now that we have our machine learning model set up, we want to train and cross-validate the network. So to do this, what we do is we take our 40 different idealized surfaces. We take 32 of those for training, and then we leave 8 surfaces out for validation of the model. And then we repeat this for 5 unique sets of validation surfaces. And we do this for different amounts of averaging and stacking. We do this for a 2D and a 3D CNN. We do this with and without the hydrogen representation, which encodes our orientational information, and we vary our grid and image sizes. And what I'm going to be talking about is the first 3, and we'll go to the results in a second. Okay, so there's a lot going on in this graph, but the y-axis tells you the root mean squared error, or the RMSE, between your INDAS calculated labels and your CNN predicted labels. The x-axis tells you different amounts of stacking or averaging time, and this is for different data representations and different types of CNNs. So the first thing that we observe is that our 3D CNN does better than our 2D CNN, which is to be expected because we also incorporate temporal correlations into our whole analysis. And we also see that our hydrogen representation does better than our stacked representation, and that is, we hypothesize that is because we also capture the notion of orientation in our input representations. And if you see your best performing representation and machine learning model, you see that if you look at the parity plot, this actually does extremely well. We get an RMSE of around 6 KT, which is higher than the INDAS RMSE, but at the same time, we get a very high rank ordering, which is a Pearson's R, which is almost close to 1. And this plot now contains 3 different kinds of end groups with scaled charges. And despite the fact that there is so much heterogeneity in the training or the test data, we see that our model performs well. And one big advantage of our model is that the time required is almost 100 times lesser than it is for INDAS simulations. So we can now use this tool to navigate like a much larger design space, which would be difficult to explore with INDAS. To do this, to use this tool and to show the power of this tool, what we do is we try to simulate different surface morphologies for a set of polar and non-polar mixed self-assembled monolayers. So the first thing that we do is we make patterns by hand. So we make a perfectly checkered or a perfectly separated or Janus-like surface of polar and non-polar groups. And the second thing that we can do is we can use an icing model to generate these same patterns. So what an icing model helps you do is that you don't need to predefine your structure, and that you can actually access a larger part of your chemically heterogeneous space compared to what you could with simply handcrafted patterns. And what we see is that the icing parameter in this case helps us control the morphology from a checkered surface or a completely mixed surface to a completely separated surface or a completely Janus-like surface as you go from a negative to a positive value. Okay, so coming to how our results look like, we predicted the hydration-free energy for these handcrafted surfaces, and what we immediately realize is that our CNN is able to capture the differences between checkered and separated surfaces, and our checkered surfaces are more hydrophilic than our separated surfaces, and that is exactly what INDAS and the 3D CNN both are able to capture, which is a positive sign. And when it comes to these icing model surfaces, what we're able to show is that again our model is able to capture the fact that your positive value icing surfaces should be more hydrophobic than your negative value icing surfaces. And we also find some non-intuitive behavior where we find some surfaces that are more hydrophilic than what your handcrafted patterns would suggest, and some surfaces that are more hydrophobic than that. and which is very interesting because this is a space that we would not have been able to explore without a fast or high throughput tool. And all of these surfaces, so there are 71 total surfaces that have gone into making this plot, and the total simulation time needed for this was less than 60 nanoseconds, which is what, say, one Indus simulation would take. So this method is extremely fast. So in conclusion, what I want you to take away is that a 3D CNN is around 100 times faster than Indus or other computational methods that people use today. Although it has a high RMSE, it has an RMSE of almost 6 kT, but at the same time it has a high Pearson's R, which makes it like a very nice high throughput screening tool for tuning the hydrophobicity of materials. And not only this, we believe that this method can be extended beyond looking at hydrophobicity, and we can also look at this method to analyze empty trajectories in other contexts. And with this, I would like to conclude by thanking all of my group members, and especially Brad Dallin, who has done a lot of the Indus simulations and the foundational work on which we apply our machine learning models. And feel free to reach out to me at kelkar2@wisc.edu for any follow-up questions and or discussing ideas. I would be more than happy to talk to all of you. Thank you so much for your attention.